Alright, if I'm expressing entire radicals as mixed radicals, there's two ways you should have learned to do it. You can either use factoring and say that, well, if I have 200, that's going to be the same as 2 times 100, 2 times 50, 2 times 25, and 5 times 5. And because it's a square root, I'm looking for sets of 2 of the same number. I have 2 2's, I have 2 5's, which means that if I take the square root of 2 times 2, I'm going to wind up with just a 2 on the outside. I will take the square root of 5 times 5, and I'm going to wind up with a 5 on the outside. And then I just have this 1, 2 that doesn't have a pair that has to stay on the inside, which means that I can say that this is going to be 10 root 2. The other way you could have done it is say, well, I'm going to factor out or see if I can divide the radicand by the largest perfect square possible. Well, the largest perfect square I can divide this by is going to be 100. So I could say that it's going to be the square root of 100 times the square root of 2. And the square root of 100 is just 10. So I get 10 root 2. Same thing holds true there. When I take a look at the second example, I have that negative on the outside, which means I still need to remember that at the end. And I can factor this down and say that I'm going to have 2 and 125, 5 and 25, and 5 and 5. Because the index is 3 in this case, I'm looking for 3 of the same number. So I have 3 5's, and I'm just left with a 2. And I also had the negative on the outside that I need to remember. So I'm going to say it's going to be negative, and then a 5 made it out, and then I have the cube root of 2 is left by itself on the inside. If I want to use the factoring method, where I'm factoring out perfect squares or perfect cubes or that, then I just need to know what the perfect cubes are that I can factor 250 by, and in this case, if I'm doing that method, I'm going to say that it's going to be negative and the cube root of 125 and the cube root of 2, which is also going to give me negative 5 and the cube root of 2. When I get to C and D, I can use the same principle that I did before. It's just when I'm dealing with the variables, I need to remember that the variable is already a certain number of whatever that number is already set. So if I'm factoring, then typically what I'm going to do is I'm going to split it up right away and say that I'm going to have 48, and I have a to the 4, and I have b to the 3. The 48 is going to be 2 and 24, 2 and 12, 2 and 6, and 2 and 3. The a to the 4 is going to just split up into 4 a's, and the b to the 3 is going to split up into 3 b's. Now I can use the same principle that we were doing with the last case. If I'm looking for the square root, I'm looking for pairs of the same number. Anything that doesn't have a pair has to remain on the inside of the radical. Anything that does have a pair, one of them can move outside the radical. So I have a 2, I have another 2, I have an A, I have another A, and I have a B that made it out. And on the inside I have 3 b's, which means that when I multiply everything back together on the outside, I have 4a squared b and the square root of 3b. I can do the same thing with the next example. I can say that 63 is going to break up into 3 and 21, and that breaks up into 3 and 7. I'm just going to list out the A's. I have 1, 2, 3, 4, 5, 6, 7 A's, and I have 1, 2, 3, 4 B's. So I have 2 3's, I have a set of A's, set of A's, set of A's, set of B's, set of B's, and I have a 7 remaining, and I have an A remaining. So what I actually have is I have 3 on the outside, I have 3 A's, I have 2 B's I'm going to move out, and then left on the inside I'm going to have 7A. Alright, if it asks us, without using technology to arrange the following real numbers in ascending order, then it's just a fancy way of saying turn all of these values into entire radicals. Because I know that if it is an entire radical, then it is going to show me exactly how big or small they are. If it's a mixed radical, you can't always tell because you're multiplying typically an irrational number by its coefficient, which could give you any range of values. So the first one I would have to deal with. The first one is just 300. For the second one, I'm going to have to multiply this in and say I'm going to have the 3 over 10 times 3 over 10 times 3,500, or 3,500 over 1. If you want to think of it that way, so you remember to multiply the numerators, which means that on the top, I'm going to have 3 times 3 times 3,500. And then I'm going to divide that 31,500 by, on the bottom, 10 times 10, which is going to be 100, which is easy enough. That's just the square root of 315. For the 18, I'm just going to say that's going to be the square root of 18 times 18, which is the square root of 324. And for the last one, I'm going to say that this is going to be the square root of 9 times 9 times 15 over 4. If it makes it easier for you, say 9 over 1 times 9 over 1 times 15 over 4. Which is going to give me 1,215 over 4, which would be the same as the square root of 303.75. As soon as I have it in this form, then I can clearly see that if I'm arranging it in ascending order, the smallest one is going to be the square root of 300. The second smallest is going to be the 9 times root 15 over 4. Then I would have 3 over 10 times the square root of 3,500. And finally, I'm going to have 18 is going to be my biggest one.